Hi, I'm Ichi, a postdoc at Southern University. I'm happy to share this project done during my internship at Meta, a Meta-Bayesian approach for rapid online parametric optimization for risk-based interactions. Risk-based input is common for AR/VR interfaces. The user experience and performance of risk-based interactions are highly influenced by the transfer functions, which are mathematical equations that map motions to the corresponding cursor positions. Take absolute pointing as example. The users move the cursor by their forearm motions. The transfer function that determines the speed of the cursor is critical for the user experience. Similarly, let's see relative pointing. The users control the cursor by their relative wrist rotations. The transfer function that maps wrist rotations to cursor movements is important as well. There are several factors that may affect the optimal system setting, including the user's physical differences, their preferential differences, reliability, and environmental factors. The optimal settings vary across different users and contexts. Identifying the optimal parameter setting is very challenging. Previous works mainly rely on manual calibration. The users need to go through an additional step prior to the intended interaction. The procedure is time-consuming and the performance is not guaranteed. The second approach is conducting human-in-the-loop optimization, which identifies the optimal setting using computational optimizations. This approach is more principled, but it is even more time-consuming, so it is not really practical. We propose Transfer Acquisition Function Plus, or TAF Plus, a Meta-Bayesian approach for rapid online parameter optimization. I'll first give an overview of Bayesian optimization and Meta-Bayesian optimization, which are the foundations of our approach. Imagine we have a very simple design task. The designer simply needs to identify the best value of one parameter. Different parameter settings lead to various user performances. And the goal is to find the setting that leads to the highest objective value. And the designer can only acquire the user performances through a sequence of evaluations. Bayesian optimization is designed for such problems. It has two core parts. The first part is a probabilistic model, or a GP model, that captures the properties of the task. It is fitted with the observations from the user evaluations. The second part is an acquisition function. It takes the probabilistic model as input and determines which parameter setting has the most potential, and that should be evaluated next. In our initial stage of the Bayesian optimization, the GP model has little information about the task. So it relies on random exploration to get more information. As Bayesian optimization accumulates more observations, the acquisition function has sufficient information to select good design candidates and converge toward optimality. Bayesian optimization has been widely applied in interaction design. However, its main limitation is still the efficiency. As we just saw, it must first accumulate information by random search before the actual optimization kicks in. Meta-Bayesian optimization tries to address this efficiency issue by using meta-learning. Meta-learning is a machine learning paradigm that learns to solve tasks efficiently by leveraging prior similar experience. Hence, the goal of Meta-Bayesian optimization is to quickly optimize using the prior similar optimization experience. Among all the Meta-Bayesian optimization methods, a more practical one is Transfer Acquisition Function, or TAF. Recall that Bayesian optimization has an acquisition function that takes the GP model as an input to determine which setting has the most potential. TAF extends this idea. Instead of just relying on the model of the current user, TAF takes prior experience into account. In the first phase, before deploying our approach on the end user, The developer runs optimization on a group of users. We call this user population users, which will give us a group of population user models. With each population model, we can query the acquisition value, which is essentially the potential value of a parameter setting. When we deploy TAF on the end user, we will also have a new acquisition function value from the new model, which has very minimum initial information. TAF aggregates all these acquisition values to determine where has the most potential to give us the best outcome. TAF merges these values based on the weights. Without going into details, it initially assigns higher weights on the prior models, so that they can guide the optimization to good start points even when we have minimum information of the new user. And gradually, it increased the weights on the new model to achieve customized design for the new user. However, TAF has two issues that forbids it to be directly applied to HCI. That motivates us to introduce our TAF Plus and its workflow. The first limitation of TAF is that it is designed only for one design objective. We address this by a novel aggregation mechanism so that the designer or the user can dynamically handle the weighting of different design objectives. This is TAF. It assumes each model only generates one acquisition value. However, in practice, we usually have multiple design objectives, so each model will generate multiple acquisition values, each corresponding to one specific objective. This is where TAF is not designed to handle. Our solution is straightforward. We first aggregate the acquisition values across different objectives by weights determined by the designer. Of course, during the deployment, the same mechanism is applied to the new user. These aggregated acquisition values then aggregates again across all the models. The benefit of this approach is that the designers can modify the weights of different design objectives whenever they like. The second limitation of TAF is that it can't actively balance the importance of the population models and the new user. Our solution is to allow the designer to proactively balance the importance of the models by adding a decay hyperparameter. The decay hyperparameter is a multiplication factor directly applied on the values of the population models, which allows this importance of these models to decay more efficiently, allowing faster adaptation for the new user. So, in short, TAF Plus has two key features. First, it allows the designer to flexibly adjust the weights of the design objectives. It also allows proactively adjusting the importance of the models, achieving even higher efficiency. We further introduced the accompanying workflow, which has three major steps. First, we run multi-objective optimization on the population users to construct population models. In our study, we gathered 14 population models. Secondly, we identify the optimal objective weight configurations based on the user preferences. More details are in the paper, but again, the designers or the users can adjust the weight during the deployments as they like. The third step is to find out the proper decay hyperparameter setting via simulations. Finally, TAF Plus is deployed on the new users or the end users. For our study, we tested it with 11 new users. Our approach is tested with two interactions. As introduced, they are absolute pointing and relative pointing. Note that these two interactions have completely different sensors and design parameters. We optimize for three objectives: completion time, aiming error, and trajectory quality. They are standard for most input interactions. Please check out our paper for more details. We compare these three adaptation approaches of TAF Plus, standard Bayesian optimization, and manual calibration. This is the resulting weighted sum performance of three approaches at each iteration. Basically, an adaptation approach is better if it reaches higher performance faster than the other approaches. You can see that Meta-BO reaches better performances than the other baselines, faster and more efficiently. Especially in absolute pointing, it starts with very high initial performance already. Here are more analysis of the performance on the individual objective metrics. For these charts, the lower value is the better. And we can see, again, that Meta-BO constantly outperforms the other methods. This is the first time we see human-in-the-loop optimization outperforms manual calibration in both efficiency and user performances. This is great because it enables the opportunity where users don't need to do any calibration, but Meta-BO do all the optimization very quickly in the background. More importantly, Meta-BO is not limited to a specific interaction. We believe this shows its potential to replace many calibration procedures in HCI in the future. We also ran a ton of technical evaluations with synthetic user functions. We learned that Meta-BO's strength is especially obvious when the problem is complex. This makes a lot of sense because complex problems simply takes more iterations for any optimization technique to solve. Meta-BO leverage the prior experience, and its advantage is more clear. We also noticed that Meta-BO performs less well when the user diversity is high. This also makes sense because essentially TAF+ relies on the shared characteristics of all the users. If the users are rather different, there's less information that it can leverage on. We also found that Meta-BO performs less well with less population models. This is again reasonable because it simply has less information to leverage on when there are just fewer population models. Finally, discussion. We anticipate Meta-BO to open new door for rapid parameter optimization for more applications, such as other input and output devices, and more design tasks, and even verifications. We see the potential where Meta-BO can replace the standard calibration procedures in various application domains. Secondly, we know that TAF+ potentially may not work that well with less population models, or when a new user is drastically different from the population users. We need more advanced technique to address this issue. To conclude, we introduce a novel Meta-BO method, TAF+, for rapid online optimization, which has a great potential to be generalized for other interactions. Secondly, we demonstrate the efficacy of TAF+ and its workflow with two representative risk-based interactions. I want to thank my wonderful co-authors for their strong support during my internship to make this project published. And thank you all for your attention.